So hey, my name is Tim Kilworth, and Subhash and I will talk today a little bit about CAN. So we understand you were interested in what CAN is, how it works, how we use it on machines, and so just some overview. So as we go through our slides, if there are questions, please feel free to shout out, and we'll kind of tune the topic a little bit as we go through if there are areas we want to talk about a bit more. But Subhash has the first set of slides. We'll talk about CAN as a technology, and then I'll go into some detail about how we use it on machines and architecture. Maybe Subhash jump to is our first slide the introduction? So I lead the electrical systems architecture group within John Deere, and my group in particular is focused on, in specific, the ag products, but in general, all of the machines. I graduated from Iowa State University way too long ago and spent 5 years first working in manufacturing, and the rest of my career has been in product design and software and electrical system design. Specifically, most of that was on tractors and most on drivetrain and operator station, and the last few years here it's been on product architecture.
Yeah, my name is Subhash Nalluri. I'm a system architect in John Deere. I graduated from Marathwada University in India. As a startup, I started working in a startup company in India, learning all about electronics and software, and then started working in a non-engineering position as assembling PCB, designing PCBs, component procurements, and then moving into engineering position, designing electronics software. So my non-engineering position did help me in better designing the electronics and the software component selections into my designs. In the last few years, I've been in product engineer for sprayers and software systems and electrical architecture, now leading the Lin, CAN, and CAN-FD technologies for the enterprise. I've been working in multiple areas, including controls, software, harnesses, and even panel designing. So, segueing into that, these are the topics that we'll be covering today. What is CAN? Controller Area Network. So it's basically on high speed. When we say high speed, it's 1 megabyte, and when you compare with Ethernet, it's nothing. But it's a lot faster for a vehicle systems. It's a high integrity, so that we'll talk about it a little later on why that integrity is there. And it's a robust communication protocol, so that really helps us. So originally developed by Robert Bosch in early 1980s for automotive industry, but then agricultural industry has adapted it, and other industries like CNF, construction and forestry also picked it up. So why we chose the CAN to be on our vehicles? It's primarily a standardized communication protocol. So there's a lot of things that's been standardized, and which makes it easier for the vendors and market to support all OEMs with the semiconductors, and all we have to do is adapt those and design around it, write your software around it. So the CAN gives you a lot of robustness in the sense that it can detect the error in the airframes or the physical layer itself, and that way the CPU doesn't have to process each and every data coming through. So all the errors, or the CPU will know whether there's an error, and it knows it, and if there's no error, then it can handle the data. And also it's a multi-drop. compared to you have a RS-232, which is point-to-point, and RS-485, which is a maybe you guys are familiar with, and 485 is a multi-drop, but it doesn't truly a multi-drop because it cannot detect if someone else is talking, and it could stomp over, but CAN does give you the benefit of it. And these are it's a progression as in 1983 the first was created, and after that the standard was updated in 91, and John Deere has gone with 2.0B, which supports the 11-bit and a 29-bit identifiers. And we use 250K and 500K extensively. Though 1 megabaud is available, but it needs a completely different physical network properties. So, but the 250K and 500K do support very close to each other. So that makes it easier for us to adapt. Any question there?
So were the only difference between the 2.0A and B the length of the identification bits?
That's correct, yeah. Okay, moving on, implement. So basically we have primarily two physical layers or standards. Within that one, they're differentiating it as a 250K that's shielded or unshielded, 500K. And these are the two standards that we will be talking about more in next few slides. And here are a few possibilities of physical bus where you could use a highly expensive shielded 2-wire or 3 wires, but in John Deere we use primarily twisted cord and twisted pair unshielded. So the twisted cord is coming from ISO, that's primarily for the agriculture, and twisted pair is recently has been added into the ISO. And we moved into the twisted pair. The biggest difference is the cost, and if you look at it, the twisted cord is $2 a foot, and compared to 75 cents a foot, and that makes a huge difference in cost. But also there's a weight compared to cord, and we had to go with the twisted cord until this new standard came in. So, and there are some standards around the length. So we say, okay, maximum is 40 meters. You can have only 30 nodes, but also it depends on how your routing is, what's your stub length, which is basically from a bus to an ECU. What's the length of those, and what's the line capacitance or the impedance in sense, because that all impacts how your quality of your signal is. And also this variable spacing between the stubs and the stub lengths would help with standing weight. And you have terminators on either end, and they have to be independent of or should not be integrated into the ECU. But you are allowed to have an integration into the ECU, but there's a limitation with that one is like if it's on a private network, 1-to-1 controller or 1-to-2, but it's still a private, and you're not allowed to have any other controllers come in and go as you please. So that's the reason it's a standard calls out that don't include it into the ECU, be flexible. Here are a few topologies that we use, but within John Deere we use only the bus topologies, And if you look at the other two, there's once you design it, it's kind of fixed and it doesn't let you, or it's not enough flexible. Whereas with the bus, you can add and remove as you need, as the system needs it. So John Deere supports only bus topology. And here's another view of the vehicle network all put together. So this is just an example of it. So you have a vehicle bus and an implement bus, and you have a subnet, implement subnets, and you have controllers connected to. These is very simplified. This is you have quite a few controllers. We have more than 100 controllers on a typical machine, but a vehicle bus is separated out and it's connected to an implement bus through a tractor or a bridge or a gateway. So you kind of isolate and say only you can have certain messages pass through. And the reason behind that one is you want the ECU, the transmission controller, hitch, which are critical for a tractor function, whereas the implement bus is more of an open so that you could add and remove or move the implements or change the configuration as you need it. So it's more of an open network implement bus. So as we segue into the data, what kind of data it goes through, if you look at it, what is the data link layer is we need a reliable transfer of data. So which includes that each CAN frame includes a synchronization, sequence control, error control, and flow controller of it. So looking at the CAN frame, you have a start, arbitration, control, data, and CRC or the trailer. So here's an example of 11-bit identifier and a 29-bit identifier. The big difference here is that identifier extension. So to begin with, the frame looks no different between 11-bit identifier and a 29-bit identifier. And the only difference is that IDE bit, 0 versus 1. And when you have a 0, means that it will be, and it will be 11-bit identifier. And if a 29-bit identifier sends a 0 in an IDE, then it will be an error, and it won't be able to send, or the receiving controller will throw out errors saying that, hey, the frame that I got is error frame. And here, this shows you further the 29-bit is divided into, and you have a priority data page, and then you have a PDUF and PDUS. PDU means it's a protocol data unit. I'll talk about those in a little bit later. But then you have a source address. So this is a standard that is a lot more flexible, and in case of 11-bit identifier, you don't have the same things. It's all you have is a number, and that's it. But with a 29-bit, you also have a source address that tells you who is sending it. And if you look at it, each bit is a 29-bit is one of it, but then you have also data. Each bit is subdivided into time quantums. I mean, the more time quantums is better, but not necessarily its advantages. But at the same time, you cannot have only few. So the time quantum is based on your clock, the CPU clock, in ratio in proportion to your baud rate. So this a bit is a 4 microseconds on a 250K baud, and if it's a 500K, it's 2, and vice versa. So, and then you have segments. So you separate into 2 segments. So Segment 1 is for positive edge errors, so there's some kind of automatic correction and clock synchronization automatically within the hardware layer. And segment 2 is for the negative synchronization, negative edge synchronization. And you have a sample point between those two. And sample point is programmable. And that's the reason where you have to have a nice finer time quantum so that you have a better support for the standard. The standard calls out for 80% of the time period to have the sample point at 80% of the time signal of this bit timing. And the sample point is primarily to detect whether a bit is a 0 or 1. At that point, it detects when it is, but it could change the states within the segment 1 time or segment 2 time, but whatever you sampled it, the sample point is the data that you're going to take. This is an example of hardware when you do look at it, or the signal on a scope. So if you look at it, ideally this runs on a 5-volt system, or 3.3 volt system too, but within John Deere we use only 5 volts. And both the signals, the CAN high and the CAN low, are biased at 250, at 2.5 volts. And as the data comes in, bit 0 or bit 1, the delta changes between these signals. That's how the controller or the hardware detects whether the bit is 0 or the bit is 1. And PDU, so you have two types of formats in here, is PDU1 and PDU2. And PDU1 is 0 to 239, that's the 8-bit that you see here. And PDU2 is 240, the rest of it to 255. The big difference is PDU1 is primarily a destination-specific message. So you have a DA that you specify in here. And with PDU2, the whole 69-bit is your identifier for this particular message. In this case, you have an identifier here with the data destination address. And of course, for both, you need to have a source address. And you have 5 different message types, is basically commands, requests, broadcast responses, acknowledge, and group functions. And when it comes to the group functions, that's where you're saying, what is this PGN, or parameter group number, which would say a number or identifier is belong to this function, or this supports these functions. That's what each one of those is. A command, there's a identifier number, which tells you this is a command message, and the data will tell you what that command is, or similar to request and things like that. And like I said, we follow 2 standards within John Deere, SAE J1939 and ISO 11783. So they're fundamentally, from a physical layer, they're the same, the signal, they're the same, but one focuses on the drivetrain, one focuses on the agriculture. One is an enclosed system. Basically, the manufacturer is designing the whole system like your car. It's not add and replace anything that you want. Whereas the ISO is an open system where a buyer, in the sense, will integrate the whole system. So in this case, like for example, you buy a computer, you buy a printer of 2 brands. As a user, you're going to be integrating in here, in this example, a tractor and an implement. It's the farmer who's going to be using them, and he is the integrator there. And if you look at parameters rule, and in ISO also we have parameters, but also there are additional things like we call it a high-level application, like bridges, the virtual terminals, task controllers, file servers, sequence controllers. And another big advantage that you see here with the ISO is, or the big difference, I should say, is ISO will support you up to 117 meg of data transfer in session in chunks, whereas SAE allows only 1785 bytes. So that's a huge difference there. And also we use that to transfer data to screens or displays with various objects of the equipment and what you want to display on. So here are a few of the differences that you could see through. One big difference I clearly show is the address assignment arbitration versus fixed. You know, here in ISO, every address you claim is, if you lose that address, you either arbitrate to a next address, available address, or you cannot participate in the system. Whereas with SAE, you design your system up, everything is fixed, and it is and in John Deere, we kind of, on the vehicle side, we use the SAE, but also we use ISO. So there are some fixed addresses like engine, transmission, but also we use the ISO standard more to support the displays, or to display certain things on that which is supported primarily within the ISO. And ISO, you could say it's primarily it's a ISO 783 is the agriculture standard. So we call that an ISO bus. The ISO bus, when we say that, is OEM is certified to be an ISO bus. It will get the stamp. Why do we have to get this ISO certification? Is basically it is speaking the same language, and like a plug and play, as in like a USB. So when you do have it, there's a fixed protocol in there. There's a flexibility of a little bit in USB side of it, of a baud rate, of a speed, but then when you look at USB 1.0, it is a fixed baud rate. So very similar to that one is you have a fixed baud rate of 250 kilo baud rate. Connectors are fixed, workflow is fixed, or standardized, I shouldn't say fixed, but it's a standardized. The advantage of that one is you have, for example, a John Deere tractor with an Case IH planter, so you could just plug in and they would work with. And without this standard, you have to have, a customer have to have a John Deere tractor and a John Deere planter, or John Deere tractor and a John Deere GPS devices. Now this will give you an interoperability and flexibility. What does it mean is you could also have an impact on your sales. You know, once it's certified, either the tractor or the implement or the components are certified, then you can sell it to any, or pitch it to any tractor owner or any implement owner, and they're not tied to that particular brand. So that gives a huge advantage in being certified to be an ISO bus equipment. And an ISO bus, like I said earlier, we have some applications that are not necessarily every equipment do support every tile here, what you see in application, but every equipment have to support 1 through 5. They have to support it. And the rest of it is if you support it, it's well and good. If you don't support it, then you would not be certified. But also it depends on the equipment that you are building on. So for example, a display will support the virtual terminal, and it may not support the sequence controller, but then it has to support file server or diagnostics. A controller could support a diagnostics and a task controller. So things like those. But in most of the ISO certified, they all support these applications. So just an example, if I don't support all the ISO standards or applications, imagine you have a cab. Every application or every equipment need their own terminal to display their data. And imagine you have a clutter of displays in your driver's seat in your car. Imagine what the distraction would be. And once you're certified, if you put in a certified equipment, a terminal in here, like one of the example is a John Deere terminal where you can see that each application has a tile by itself, and you have an equipment here, they have their own tiles, and when you click on it, you get their own application. So in here, there's a sprayer, so you click on it, and then you have buttons when they are related to this particular application, they are programmable. These are all part of standard, but the design or the fonts is also controlled part of the standard, so you could control it in there. So here is another example of a John Deere display with ag leader application. Though they have their own fonts, they control their own everything. That's the working area that you have in the left. But the buttons or the tiles, these are all designed specific for John Deere, and John Deere chose to do in this fashion. And the buttons, the application would tell you which button and what they meant and what the graphics should be. So that's, again, it's part of the standard that it gives you the flexibility of how to do it. And you see that Horsch has a different approach to this. Instead of soft buttons, they made it a hard buttons. And if you look at Ag Leader, they have their own screen, and there are plenty of terminal manufacturers, and they have their own style of executing it. In this case, everything is, there's no buttons or you don't see it, and there are hidden buttons or like this, they pop in and go out, and it's their design. But still, all these graphics could be, even if I can put a John Deere display and I can get all of these in on the screen. And as a part of the ISO bus, you also have to meet this standard in connector standard. So the left, the connector is IVBC. That's the implement bus breakaway connector. So this one is, for example, you disconnected the hitch and you forgot to disconnect your electrical, and the tractor, you drive over the tractor. So what we want is this connector will break away automatically without destroying your wiring harness. These put together, so that's the pinout of it. And then you have a diagnostics. This could be in the cab or on the implement itself. This is a standard again. It supports 2 cans, and power supply in there. So that the connecting device, which is for diagnostics or programming, can talk to the controllers and program them or diagnose it. And this is an ISO aux connector, we call it aux connector. This usually it's in the cab, used for connecting a joystick. So for example, an equipment may need special joysticks, and the joystick may not be supported by a particular tractor, and they can connect their own joystick here and remove it. And when the next equipment come in, if they want their own joystick, they can remove the first one and put the new one in. So that's the part of the standard and part of the protocols. All these are put together. So this is just the CAN Classic, or we call it a CAN Classic. But the next thing is we'll be looking at is the CAN FD, so flex data rate. And this is built on CAN Classic, except the big difference is the payload size. When we say payload size, is the data packet size. And at what speed you want to send that. Or you have a fix, you design a particular speed, and all controllers have to support that speed. You cannot have one controller having one speed and another controller having a different speed, so that's not allowed. This was first developed by Robert Bosch in 2012, and then it's standardized after that in 2015. And to give you an idea what a CAN FD frame would look like, or at least the standard is, like I said, it's built on CAN FD, and you can see that arbitration, the data, the basic structure is still the same, including CAN FD. Here I'm showing you only 29-bit, but then the CAN FD supports between 11-bit and 29-bit identifier too. So in a 29-bit, you could see that Classic look the same. The only difference is that R0, that's a reserved bit 0 and reserved bit 1. So that gets flipped. So 0 here to 1. And that tells the low-level drivers or the hardware drivers, hey, there's an FD frame, so I should be ready with that. And you also have to tell whether you have a higher baud rate data frame coming in. So the big difference that you could see here is 8-byte versus the 64-byte. And what the advantage there is, so if you look at on a CAN frame, and let's take a 29-bit CAN frame with an 8-byte. So you have an overhead of 29-bit. And if I take the same thing and say add 64-bit, that means that I'm at 64 bytes and I have 8 additional, or 8 times the data that I'm sending with a one header or one size of header, which means that I'm gaining 7 times the data. So when you look at it, you can send a 4 megabyte in 35 seconds compared to CAN Classic of 142 seconds. That's a huge difference. And also you have, you could use the CAN FD for your programming. That gives you an advantage there, a little faster there. And also you could use it for backing up security part of it, or use 64 bytes or the rest of the 64 minus the 8-byte data for any security, or you could put the whole thing as a data. For example, in a programming, you could send as the complete data there. And in a different perspective, all we're changing is the header stays the same, the trailer stays the same, but the payload is the one that we're changing. And in a different view, this gives you a different perspective of it. CAN Classic, if you look at it, it takes X seconds to send us data for that particular data. And CAN-FD can do it in X by 8 seconds. And coming to the same FD of a 64 byte, you can do it in X seconds. So you're gaining, you're sending 7 times more data, or a total of 8 times. Now, if I put this same thing, looking at the same network diagram of this vehicle, can I take this one, because everything else is the same. The CAN-FD, it's using the CAN Classic, 250 versus 500, it's using the same. Can I just simply change it to CAN-FD? No, it's not that simple, because CAN-FD, you have to design the controllers to support the CAN-FD, which means that the low-level hardware should support the CAN-FD. Either it's tolerant so that it doesn't throw errors, or it is compliant so that it can read it and understand it and respond to it. You also need to update the software. And since here is to understand the CAN-FD frames and to handle the data, the additional data that you can get it in that. And also, of course, the memory, because you have to, certainly you have more data coming in the same time frame, so you should be able to also handle that. So when we say a higher baud rate, so within John Deere, we chose to stay with 2 megabaud. So the CAN-FD frame with the flex rate, in John Deere, we decided to go with 500K and 2 megabaud is the standard that we chose to within the John Deere. And follow-up is network security. But if you have any questions on the hardware side of it. If not, Tim?
Yeah, I had one quick one.
Yeah,
If you want to go back one slide. So with the multiple networks, are like, I don't know, packets, I want to call them packets, from like, say, the computer management able to get to like the hitch controller, or does it just, like, there's no forwarding between the networks?
There is forwarding, but we design it which one should be and which one shouldn't be between the vehicle bus and the implement bus. But all the controllers on a particular bus have access to it. And it depends on your software design whether you want to read a particular message or you want to filter it out at the hardware level itself, so that the CPU is not interpreted. Sorry, did I answer your question?
Yeah, I just had a quick follow-up. So like the, was it the authenticator, the identification bits is what determines whether or not it gets forwarded?
That's correct.
Okay, thank you.
Yep. Tim?
You bet. Go on to start the next slide, Sahit, or Savash. So I'll talk about a couple topics. One is security challenges with CAN, and then a little bit about how CAN and networks impact the overall machine architecture. Kind of like the network diagram that Subhash just showed, but maybe a couple more points about it to go forward. But go ahead and go to this slide here. So one of the key, or one of the aspects that was requested was about how can we do any integrity, data integrity across CAN? And really the answer is it's pretty limited. the packet length of 8 bytes per packet is really hard. We looked at it, and maybe we could get that secured signing down to about 7 bytes with a freshness counter and a tag, but really getting it much less than that, then we started losing up some of our security capabilities. And of course, if we're limited to 8 bytes, then there's not a lot we can do. The mitigation for this then would be to switch to a different technology. Subhash talked about CAN-FD, and that has up to 64 bytes of data per message. And so if we switch the technology to CAN-FD, we can still have the advantages of CAN. We have to be a little bit more concerned about electromagnetic interference because the higher data rates, especially where machines are operating outside in the wild and electrical power lines and other systems around, we have to be concerned about that. Or the other one is switching to an Ethernet technology, and there's some different Ethernet technologies that we didn't cover. So there's a traditional 4-wire twisted pair, or there's an automotive standard for an automotive style Ethernet that is 2-wire twisted pair for 100 megabit. That's interesting to us as well. But in that case, you could get up to 1,500 bytes per packet and do some security there. The other challenge we run into, especially on the vehicle side, is the microcontrollers that we use are really more focused on real-time control. 16-bit and 8-bit are still widely popular, although 32-bit is starting to surpass those. But all of those micros are traditionally a single core, and so you're trying to do cryptographic math and machine control in the same space, and that doesn't really work so well. And so getting both of those, getting the micro updated, the newer micros have what's called an HSM, or a hardware security module. It's a standard in the industry for real-time controllers, microcontrollers, to be able to do cryptographic math in its own core, and oftentimes there's some hardware acceleration in there as well. So if we just take a look at a machine today and we wanted to secure it, yeah, the network layer and the microcontroller layer, and beyond that, the software layer, really are strikes against that. But as we look at new technologies and future designs, looking at CAN-FD, Ethernet, new micros, new software, and the hardware security module to be able to add security, add security to new machines. So Subhash, maybe jump to the next, and with our time, let's build this out a couple more slides. So one of the areas that's coming in automotive that actually most of the ag industry has been at for a while is this idea of a sensor layer and a services layer in the architecture. So if you think about the technologies and the purposes that you want on the machine, the signal layer is really all about signals. That set of technologies is really great at reading signals and processing signals, setting actuators and real-time control down to the millisecond control. The layer above it is more at a services layer. So we want to add and subtract features to a car real-time, or to a tractor real-time, and be able to have features come out more at a releasing software and releasing new features a few times a year, and both for automotive and for the ag industry. Now the diagram that Subhash had there on the right, showing the virtual terminal and the gateway, and those capabilities are more of the services layer. And when you think about real-time control of a hitch or an engine controller or an implement, more on the signal layer and the control level. Kind of some differences between these two. So both sides of that layer have a lot of value in software and growth in software. So as we continue to add new sensors, new actuators, new control capabilities to machines, a lot of value there in the software. But as you think about the value in changing that software, so oftentimes, a transmission software is going to impact the durability of the transmission. So when we go through and we test those systems, we release them, we release the transmission controller software, and the transmission is a matched set. And really, there's not as much value in changing that transmission controller software because it's so tightly coupled with the hardware. So really limited value for changing the software in those components. But if we think about the services layer, well, that's where we can add things like, smart machine control, guidance, GPS guidance. The management computer can send down a map of the field that you're going to plant, and it can have what's called a prescription, so you can vary the seeding rate and the fertilizer rate across the field, and then the machine can gather that data and send that back up. So that's not as closely coupled to the machine itself or to the capabilities of the machine as it is about managing the interface between those two and adding capability to the services layer. So those two layers, that when you think about where we would apply Ethernet and where we would apply CAN and CAN-FD, the services layer is more Ethernet and has been entrenched in Ethernet for a long time. The signal layer is more CAN and CAN-FD for the technologies that we use there. And I think I just have one slide, and then we can go to the question and answers. So another aspect of this is the domain architecture that's coming in all vehicles, automotive, off-road, and on-road. Really about decomposing the machine down into functions, and this is kind of where systems engineering is playing a really strong role here. So thinking about the machine as a system composed of subsystems, being able to decompose the machine down into different functions, and having a kind of a robust network design where the backbone is probably more CAN and CAN-FD today and moving more towards Ethernet in the future, and being able to have a faster and more robust connection to the outside world. And then the subnets staying at the technologies that we just talked through of CAN and CAN-FD. Probably some LIN, which is a local interchange network. FlexRay is an automotive technology that we don't use as much, but another real-time networking. And then some of the automotive Ethernet may be interesting as we get to more high-speed control algorithms and needing low latency, high-speed control to the subnetworks. But with that, we wanted to leave some time at the end if there are any questions for either Subhash or myself.
Someone should have some questions.
So I remember the last time you guys came in, you talked about one of the challenges you guys were looking at for security-wise is I think you went over like GPAC, and then particularly it was GPAC 2 had come out. I think it might have been like a year or two before that particular presentation. Are things like CAN-FD addressing the issues that the CAN bus had that allowed for like GPAC 2? So if I remember that particular exploit, that was the one where the CAN bus checked particular signals at particular times in order to see that they were the correct signals being sent by the actual bus itself and not interference from somewhere else. And you could kind of trick it by getting like as close as possible to that time, but not quite, and sending a signal. Does that kind of ring a bell?
So that might have been a couple of other folks that talked about that, but in general, the capabilities we get with CAN, and really it's not necessarily CAN or CAN-FD as much as it is the packet lane, and being able to have each message come in and be able to authenticate it. So like an engine controller, engine speed comes out by the standard every 10 milliseconds, and so as we receive those messages, we want to be able to verify that the message came out, that it was from the engine controller that we expected, and the message is authenticated and not somebody who's doing like a piggyback attack or a man-in-the-middle attack. But that gets us the next step in the capabilities that we'd want in the network for those real-time control messages and the data that we'd want to send. So I think what you kind of described was a piggyback attack, similar to that, yeah. or maybe a man in the middle. The piggyback attack is is easier because with CAN, because sometimes the messages are coming out once per second. So you've got a long time if you just sneak your message in as right after that one message comes out, then whoever reads that will believe it. But if it's been signed, we know that it has the freshness counter, and the freshness counter is incrementing the right way, and that it's been tagged, and we have a lot more confidence that it is the right message from the right sender.
Yeah, that's what I was thinking. You guys were going to kind of go with the expanded packet length, because that was kind of the big issue back then, was that the packet lengths were so small it was hard to actually get anything in there to kind of certify the messages and make sure that they were actually coming from the correct places. So
absolutely.
Yeah, that's where the CAN-FD do help. But I just want to, I forgot to mention this, is within John Deere, we chose to stick with the 32 bytes when we're sending a signal. So 32 bytes at a higher baud rate, so that 500K 2M, it fits within the same time frame as an 8-byte regular frame. And 64 bytes will be used mainly for the diagnostics and programming. That's the strategic decision that we took, so that we were not disturbing the current CAN frame timing on the bus, so that the controllers that they are waiting for it to transmit, they won't be pushed back in time, or their messages would not be pushed back too far out. And so that's the reason we chose 32. And like I said, what Tim was mentioning about is that freshness value and all of that is you work with the rest of the bytes after you send the 8 data bytes. So you have 24 bytes of whatever you want to send it as for authentication, freshness, and everything else. Tag.
Good question. Any other questions?
I was a little bit curious. So you had mentioned that there would be CAN buses on the sensor level, and then you'd be using more Ethernet at the higher service level. Is that more of like a cost thing, or was there something else that I missed?
The cost is one of the drivers, but also it's the machine needs and the networks. So CAN is, I mean, the reason why it's been around since 1991 is because it does an awesome job at real-time control. So low latency, high integrity. We know that regardless of maybe independent of somebody tampering with it, we know that if the message comes through, the data in that message is right. It's very robust, that if there's noise or any other interference with the message, that it comes through. And Ethernet is, the other aspect of this is the micros and the processors that are supporting these. The real-time control, the microcontrollers, it's much easier to find microcontrollers with automotive ratings, and automotive ratings being temperature and reliability are two big key things for automotive rating on a micro. To be able to get those that actually support Ethernet is just coming out, or maybe in the last few years is becoming more popular as the automotive style Ethernet is becoming more widely available. So that's the other aspect of it is the availability of the parts, and cost always seems like maybe a reason that's not as, let's say, prevalent or as much of an engineering basis. But when you look at Ethernet, putting Ethernet connectors on a machine to last the vibration, to last the life, to go through temperature cycles, because the technology we put on the machines on all cars and all off-road machines has to survive and work at minus 40 up to 40 and even up to like 125, depending upon, and talking about temperature in C. So really high temperature depending upon where it's mounted at. And so getting a technology and connector system that will survive that becomes really expensive. Like a single connector, gosh, Subash, an Ethernet connector, traditional Ethernet that would last the lifetime of the machine is $20 for one connector.
Yeah, exactly. When compared to the CAN is only a few pennies, and you could integrate into an existing connector and it will work as long as you meet certain guidelines.
Yeah.
And also, if you look at Ethernet, is a point-to-point, so which means that you have to add a switch. That's an additional hardware expense, and everything adds up. And so, if you look at it, that probably the Ethernet might be a good one for your backbone, and maybe in certain applications. But as you see in this diagram, various domains and the domains underneath that, they may choose to have just a CAN or CAN-FD or even LIN and not choose to have an Ethernet and get all the signals, or for that particular domain, you control everything out and then send only the data that's required for another domain, like a chassis to a powertrain domain or a body domain. So you have to balance the cost to the benefit and the requirement itself. Is this a time critical, or is it the data critical? The amount of data. So again, it depends on the application.
Another aspect about machine design that's not often thought about, but by far the most expensive, if we think about like a machine that, Subash, if you go back to that diagram that you had, so by far the most expensive component on those machines are not the controllers, it's the harnesses. So harnesses, getting production harnesses that will meet the needs and connecting to all the sensors, routing them back to the controllers, they'll cost a lot more than the controllers will on any machine. So oftentimes we try and optimize controller cost and, trying to balance an expensive solution because we want the customers to purchase the machine, so we don't want to make them too expensive. And then with what the capabilities have and even the capability of CAN is probably still a more capable real-time network for the needs we have, and Ethernet is coming up fast too. Both for the capability that the controllers will have, but also from the capability itself.
Yeah, for example, cameras. Yeah, for example, cameras. You want to add some cameras on your system, and you want to see it on your screen in the cab. Well, you have. What is the best way? CAN is not the best way for the camera data to be transmitted. So there you have an Ethernet that you could use. And by the way, you have an Ethernet, maybe you could send some high-speed data on that one, or a large chunk of data that you have to transfer and over the Ethernet rather than choosing a CAN.
Yeah. Another aspect of it is the microcontrollers themselves. So a CAN network, if we're having a message come out on a heavily loaded bus every couple milliseconds, having the messages come out that fast is no problem for the microcontrollers that we would use. They would, whenever a message comes in, we buffer it and then process it shortly thereafter. So being able to handle the network and handle each individual message that we would have is not an issue. If we look at some of the processors that are used at the above in the services layer, we always have to have an interface to be able to handle CAN, because those processors aren't very good at being interrupted every few milliseconds or even within a millisecond to handle the messages, and you can really eat up a lot of overhead in how CAN is handled on those processors. So while they're really great and the infrastructure is set up well for those to handle Ethernet, that's not so much for CAN. And like I said, until recently, the lower level microcontrollers that we have on the devices themselves are or just recently, it's in the last few years, able to handle Ethernet.